Today we're going to talk about composing functions, finding the inverses of functions, and also the difference quotient, which is just fancy words for slope, but it's a little more complicated. So let's talk about the following two functions. We've got f of x equal to x cubed minus 2x and g of x equal to 4x minus 5. And I'm going to try and use some colors here to kind of differentiate things. So we'll think about this one in blue here, and red. Not that it's super important, but it's a little important. So we've kind of danced around this function notation for a while. I've used it off and on, even though I haven't been particularly explanatory about it. But it's just an easier way to write a function. So you could totally write y equals x cubed minus 2x. If you wanted to find out what y was equal to when x was equal to 2, you could say x equals 2 and y equals 2 cubed minus 2 times 2. But it's kind of a lot to write. So one of the kind of great things about function notation is instead of saying all that, I can write f of 2 and then just plug in 2 for x and say f of 2 is 2 cubed minus 2 times 2. So f of 2 is equal to what, 8 minus 4, which is just 4. And what's nice about this notation is that this tells you that when x is 2, y is 4. So all of that information is in that small statement there, instead of having to write x equals 2 and y equals f of 2 equal to 4. So that's kind of what's convenient about it. And then the idea here is really just to get comfortable with the fact that when you're evaluating the function at a point, you're just plugging that point in for every variable. You all the attendance form again. So I want to find g of 1, same idea. I'm just taking g of the function g, which is 4x minus 5, and substituting in 1, 4, 4. One of my students, when they told me how they did this, they said they just like to write, instead of writing 4x minus 5, they like to write a parentheses wherever they had an x. Kind of like that, and then substitute in what's in the parentheses. In this case, a 1. That's going to be 4 times 1 minus 5, which is 4 minus 5, which is negative 1. So g of 1 equals negative 1. I don't really need to put that in the box, but I'm going to because I did for the other ones, so why not? It gets a little more complicated when you have a composition of functions. So f of g of 1 says we're trying to find, well, we're first trying to find, I think you should think of it from the inside out. So we're going to look at g of 1 first, and then we're going to do f of that. We just calculated g of 1, it was negative 1. So we could think of f of g of 1 as, well, f of x is x cubed minus 2x. So actually, I'm kind of going backwards there. I want to work from the inside out, not from the outside in, although you can do it either way. I want to think of this as f of g of 1, which is negative 1, just from the work we already did. And now I'm going to say, well, f of x is x cubed minus 2x. So f of parentheses is parentheses cubed minus 2 times parentheses. And then I'm just substituting in the negative 1. Negative 1 cubed is negative 1. Minus 2 times negative 1 is plus 2. So negative 1 plus 2 is positive 1. This is not the only way to do this. Some people do kind of like to see it the other way. So you totally could, if you wanted to, work from the outside in. It's not my preference. It's not most people's preference. But you could think of this as, well, I have f of something. So f of g of 1 is my something cubed minus 2 times my something, where the something is g of 1. That is also a valid way to look at it. And then you say, oh, g of 1 is negative 1, and then you get the same thing. You get negative 1 cubed minus 2 times negative 1. I don't particularly recommend that, but that doesn't mean it's not right. So you can totally work from the outside in or from the inside out. Most of the times with the composition of functions, we usually work from the inside out. Here's what I mean by that. So if I want to find what g of f of x is, now, first of all, everything we've looked at so far, we've just gotten a numeric value. We plugged in the number, we've gotten out a number. And now we're not plugging in a number, we're just trying to see what the composition of functions looks like as a function. So we can work from the inside out. So I'm going to rewrite this instead of as g of f of x, I'm going to write it as g of, and I leave myself enough room. Yeah, it's enough room, barely. X cubed minus 2x. Just replacing the inside stuff with what it's equal to. And then I'm going to say, well, I know that g of x is 4x minus 5. So g of some new thing is 4 times that new thing minus 5. And then the inside thing is still x cubed minus 2x. As far as we're concerned, you could leave it like this. Especially, most of you are probably going to take a class next quarter where you're using web work. Not everyone uses web work, but a lot of people use web work. And you should be aware that web work doesn't really care if you simplify your answers or not. They do care if they're precise, meaning you often don't want to use decimal approximations if you're finding numbers. But as far as like writing your answer, you could totally write it like this, or you could multiply it out and simplify it and say, which is what we should do, and get 4x cubed minus 8x minus 5. To me, this is the preferred simplified answer. But yeah, you're going to probably be in an environment where writing something like this is totally acceptable. Okay, now let's look at the other one, f of g of x. So again, same idea. I'm going to take my inner function g of x and replace it with what it's equal to. So f of g of x is going to become f of 4x minus 5. And then we're going to say, well, I know that f of x is x cubed minus 2x. So f of some new stuff is that new stuff cubed minus 2 times that new stuff. I'm always, bless you, I'm often thinking of the inside function as some stuff. And that's an idea that I would encourage you to hold on to into calculus, especially when you start learning about the chain rule, which I know is a calculus thing, but it's coming in your future. Next quarter, chain rule, you'll be all over it. So when you learn about the chain rule next quarter, think of the inside function as some stuff. And we'll talk about, well, you won't talk with either whoever's co-class here, and we'll talk about, they'll use the word stuff too. We all like to use the word stuff. It's a great word. Best word ever for the inside stuff. Here I'm going to have 4x minus 5 cubed minus 2 times 4x minus 5. And here's a place where I would probably prefer not to multiply it out because it's kind of a pain. But we're going to multiply it out anyway. So when you multiply something like this cubed, I think we've talked about cubes before. So if you have, like, for example, just so everyone knows, a minus b cubed is just a cubed minus 3a squared b plus 3ab squared minus b cubed. So here we're going to have the first thing cubed is going to be 4x quantity cubed. And then we're going to have minus 3 times 4x squared times 5. And then plus 3 times 4x times 5 squared. And then finally, minus 5 cubed. That's all of this. And then we have a minus 2 times 4x and a minus 2 times minus 5. To simplify, right? So you might see here a great example of where you should definitely, if this was an answer you're finding in web work, leaving it like this is probably preferable. We don't need to multiply this all out, really. But we're going to because it's good practice. 4x cubed, 4 cubed is 64. Ooh, 4 squared is 16. 16 times 5 is 80. 80 times 3 is 240. So you get minus 240x squared. And then 5 squared is 25. 25 times 4 is 100. 100 times 3 is 300. And then 5 cubed is 125. Minus 8x plus 10. And finally, combining like terms, we've got 64x cubed minus 240x squared. 300 minus 8 is 292x. And minus 125 plus 10 is minus 115. The point of this question, though, is not really to do the simplification we just did. It's more to be able to correctly input this 4x minus 5 into the argument of the other function f of x. So being able to see, oh, that's what we've got. That's what's kind of the most important thing about this process. The other thing, so one reason we did simplify this, though, just so we can be absolutely sure, is I want to stress g of f of x and f of g of x are very much not the same. Right, those are very, very different functions. I mean, they're not so different, they're both cubic functions, but they're still different enough, right, that they're not the same. And in general, when you compose functions in the opposite order, g of f of x versus f of g of x, typically they are not equal to each other. There are some exceptions to that, they're rare. But one of the exceptions that we actually care about is what we're going to talk about today, which is functions being inverse functions. So two functions are inverses if their composition, if the inverse compositions not only are equal to each other, but are equal to x. So two functions of inverses is if f of g of x equals x, and if g of f of x equals x. And the idea that we should be thinking about here is that essentially, if f of g of x equals x, the functions f and the functions g have undone what the other one does. So you started with some x, g of x did something to it, and then f of that got you back to where you started. So that f of g of x ends up equaling just x. And similarly, g of f of x is also going to equal x. Let's look at an example. Let me make sure I'm looking at my notes. I'm not forgetting to say anything important. That's fine. Cool. So let's look at this example, which is not my favorite example, I will be perfectly honest, but it's still a good example. F of x equal to the square root of x and g of x equal to x squared are inverse functions as long as x is positive. Or non-negative, I should really say. But let's actually take a look at it. So let's show it. So f of g of x is f of x squared, just replacing g of x with what it's equal to. And then f of something is the square root of something. So f of x squared is the square root of, I'm just plugging in the x squared there. Now, we've talked a lot about the square root of x squared in this class. What's the square root of x squared equal to? Or are we in this class? I know I have many of my classes anyway. What is the square root of x squared? Well, so yes, in this case it is x. I will tell you more generally, it's actually the absolute value of x. Because if x was negative, you can still take the square root of x squared and get something out that was positive. But that's not really what's important here because we're already assuming that x is positive. So the square root of x squared is just x, which is what we expected to happen, right? We expected that these functions are inverses. So f of g of x should get you back to just x. Here's, well, in fact, plus you again. So let me show you an example. Let's say we had x equal to 9. G of x, or g of 9, is equal to 9 squared, which is 81. And then f of g of 9, my 9's kind of look like my g, sorry about that, is equal to f of 81, but f of x is the square root of x, so f of 81 is the square root of 81. And what's the square root of 81? 9, exactly. So the whole point is, for inverse functions, g did something to your input, took you to some place, and then f totally undid what g just did. G took the value, squared it, f took that squared value and undid it by square rooting it. That is the total story, right? I mean, there's more complicated functions, but that's really the whole story when it comes to inverses. One function did a thing, the other function, its inverse, undid that thing and got you back to where you started. Let me say it like 10 more times, but that's the idea, is that they are undoing each other. So in a similar way, g of f of x is equal to g of the square root of x, which is equal to, well, g of x is x squared, so g of some stuff is some stuff squared. And the square root of x squared is just x. So that is typically how we show that functions are inverses, by showing that both f of g of x is equal to x and g of f of x is equal to x. Let's look at a couple more examples. Also I should point out, because it is worth seeing, that graphically inverse functions have some neat things going on. Do I have this on my? No, it's not. Okay, cool. So if we were to graph both of these, when x is positive, I'm just going to graph it up here because I've got some room. So let's say here's f of x, the square root of x. It looks kind of like this. And g of x, which is x squared, except x has to be greater than or equal to 0. So just the right half of the parabola looks like this. And the thing that's true about inverse functions graphically is they look like reflections of each other across the line y equals x. If you were to draw the line y equals x, these two functions look like mirror images of each other in that line. And that is always true for inverse functions. Let's look at a few more examples. An example we're already kind of familiar with, e to the x and natural log of x. So we can show their inverses. It's certainly true that f of g of x is equal to f of the natural log of x, which is equal to e to the natural log of x. And it's certainly the case that e to the natural log of x is just x. Really what I should be saying here is the natural log function is defined as the inverse of e to the x, right? We got a natural log or a logarithmic function because it is, someone said, I want to have an inverse of this exponential function. So we kind of said, well, I'm going to just create this other thing that happens to be the thing I want. So it's definitely true that they're inverses of each other. So when you compose them, you definitely get x. Now, this might feel a little dicey to you, but it is true because you're saying e to the thing. If you take, well, natural log of x is e to what power equals x, and we're saying e to the thing, that if you raise e to that power, you get x, well, then you get x. I know it's a lot of words, but those are what the words mean. The other direction is a little nicer, I think. G of f of x is g of e to the x, which is the natural log of e to the x. And you could bring the x down if you wanted to. You don't have to, though. You could just say, I've got e to the what equals e to the x. Oh, it's got to be x. Definitely inverse functions. And they definitely have the symmetry across the line y equals x. We draw them. Here's my f of x in blue, e to the x, going to the point 0, 1. I mean, we've seen this, when we graphed logarithms and exponentials before, we saw this symmetry before, but it's good to see it again. So here's f of x, and then natural log of x goes to the point 1, 0. Looks like this. There's definitely the symmetry that we're talking about. You reflect these in the line y equals x, as long as you've drawn them decently. They look like mirror images of each other. We got one more example. Well, actually, so this next example is slightly different. So the first two say they're inverses. The third is actually phrased as a question. Are these functions inverses? So the way we typically show functions are inverses is by doing this. We show that f of g of x is equal to x, and you also do have to show that the other composition is equal to x as well, because sometimes you can get it to work one way and not the other way. It's kind of atypical, but it can happen. So let's look at f of g of x. It's going to be a little gross. So f of g of x is f of 2x plus 4 over 3, which is, so I'm going to take my function f of x, which is 3 times x minus 4 over 2, and write it as 3 times parentheses minus 4 over 2. And then I'm going to plug in the 2x plus 4 over 3. Okay. Something I want to make sure that you do when you do a problem like this. You can't just cancel everything out at once. You have to be a little bit orderly about the order in which we cancel things. So looking at this expression, what do I have to cancel first? Got to be the 3s. 3 divided by 3 cancels out. So then you're left with 2x plus 4 minus 4 over 2. Then 4 minus 4 is 0. Those cancel. And then you're left with 2x divided by 2, and 2 divided by 2 is 1. So you've got 1 times x, which is just x. Great, like we thought it should be. Versus the other way, g of f of x, same kind of idea. You're going to get g of 3x minus 4 over 2. And then g of x is 2x plus 4 over 3. So g of some stuff is 2 times that stuff plus 4 over 3. I really do recommend, when you're doing this kind of thing, writing g of whatever as just each x thing you've got, giving yourself a parentheses instead. I think it really makes it easier to see that we're putting in a new thing for x. So here I'm going to have 2 times, that's just going to go right in there. 3x minus 4 over 2. And then we can cancel the 2's and say we've got 3x minus 4 plus 4 over 3. And then we can cancel the 4's. So we've got 3x over 3. And then we can cancel the 3's and say we've just got x. I do really want to see all 4 of those steps, or however many steps are there. The issue with kind of canceling everything out at once is sometimes they don't all just cancel out the right way. If you can't, so just be careful is all I'm trying to say, is be careful. Oh, somewhat interesting, I think, is sometimes you can kind of say the words to yourself that allow you to see that these are inverse functions. Because if they're not too terrible, you can kind of say that an inverse function undoes what the other one does by undoing the operations in the opposite order. So when I look at this first function, f of x, I'm seeing, well, first I'm doing 3 times x, and then subtracting 4, and then dividing by 2. And g of x exactly undoes all those things in the opposite order. So g of x first takes x and multiplies by 2, which undoes the division by 2, and then adds 4, which undoes the subtraction of 4, and then divides by 3, which undoes the multiplying by 3. So they really are undoing what the other one does. Some other functions that are more complicated, it's harder to kind of talk it out like that. But for nice linear ones like this, you can really see that you're just undoing what the other one does. I should also say, I strongly discourage you to think of them as canceling out. They're really not canceling, right? I know a lot of times people like e to the natural log of x and they cancel the e in the natural log and say you just got x. But I really want to emphasize, try to say the words they undo each other to yourself, because that's a more correct way of thinking about it. That's going to lead to better things later on. So inverse functions, they really undo each other. They don't just cancel each other out. So the other part about inverse functions is, how do we actually find them, right? So typically the process for finding the inverse function is you switch x and y. And that's kind of the most important part. It's really easy to do, but when you're inverting a function, you are literally interchanging the roles of the inputs and the outputs. So just to kind of go back for a second, sorry, I know I just do all this, but I just want to point out here, for this function here, if I say, do that right? Yeah. I just want to say that if I plug in, I don't know, let's say I plug in 6 for x in f of x. So f of 6 is equal to 3 times 6 minus 4 over 2, which is 18 minus 4, which is 14, over 2, which is 7. And then on the other hand, if I plug in 7 for g, g of 7 is equal to 2 times 7 plus 4 over 3, which is 14 plus 4, which is 18 over 3, which is 6. So the whole, another thing to see about inverse functions is they really do interchange the role of x and y. Here I'm inputting an x value of 6 and getting out a y value of 7. Here I'm inputting an x value of 7 and getting out a y value of 6. So when you find an inverse function, even though it's the easiest thing to do, the part where you interchange x and y is actually the most important part. Yeah, there's some algebra we have to do after that, and it is important as well. But really, the second step, I guess, because the first step I usually do is I rewrite it as y equal to 4x cubed plus 1. But then this second step, where we're going to interchange x and y, meaning the only y you have should become an x, and every x you have, because you might have more than one x, becomes a y. That was a joke about dating too much earlier, but I missed it. And then after that, so that's the hard, well, that's the easy part. The next part is the less important, but still important, harder part, where we solve for y. So here I'm going to subtract 1 from both sides. X minus 1 equals 4y cubed. And then I'm going to divide both sides by 4. X minus 1 divided by 4 equals y cubed. And then I'm going to take the cube root of both sides. Let's say that the cube root of x minus 1 divided by 4 is equal to y. And lastly, although this last step is not super duper important, but it is moderately important, we rewrite it as, instead of writing it as y equal to, we rewrite it as f inverse of x equal to the cube root of x minus 1 over 4. That is the notation for an inverse function. It's an f with a superscript -1 of x. We don't say f to the -1 power of x. We really do just say the words f inverse of x. That is the way you should read that notation there. I also want to stress f inverse of x does not equal 1 over f of x. Not a reciprocal function. It is the function that undoes what the other one does. And we can see that right here, definitely the inverse function wasn't 1 over 4x cubed plus 1. It was the cube root of x minus 1 over 4. And these functions totally undo each other. Also, this is another example of when you can kind of talk it out. F of x takes x, cubes it, multiplies it by 4, and then adds 1. Whereas f inverse totally undoes all those things. First, it subtracts off the 1, then it divides by the 4, then it takes the cube root. Undoes all the things we just did in the opposite order. This next one is probably the hardest one to actually kind of do algebraically because it requires a little bit of extra work. But let's do it. So step 1, I'm going to write the step 1's kind of a nothing step. You could call it step 0. Rewrite it as y equals. I mean, you could totally use f of x if you want to. It's just f of x is a little more cumbersome to work with algebraically. So I would write it as y. So y equals 2x plus 3 over x minus 4. And then the all-important step of interchanging x's and y's. So x equals 2y plus 3 over y minus 4. So all the y's become x's, all the x's become y's. Okay, now the hard part. We got to solve for y. This is where we have to be a little extra careful here. I guess I could do this up here. So first things first, I'm going to multiply both sides by y minus 4. So y minus 4 times x equals 2y plus 3 over y minus 4 times y minus 4. And the reason we're doing that is because we really would prefer not to have any denominators, at least for now. Here's where people usually take a wrong turn, if they're going to take a wrong turn. We have to solve for y. But we have to solve for y, and our answer has to not have any y's in it. So to make that happen, we have to be able to get all the terms that have a y on the same side of the equation. So we have to distribute this x and get x times y minus 4 times x equals 2y plus 3. And then everything that has a y in it, specifically x times y and 2 times y, need to end up on the same side of the equation. So I'm going to bring them all to the left, although you could totally pick the right. So x times y minus 2 times y equals, and then I'm bringing everything else to the other side. So I'm going to bring the negative 4x over to the other side along with the positive 3. So I'm going to have a 4x on the other side because I added 4x to both sides plus 3. Now that we have all the things that have y on one side, we can factor out a y, which is why we did that. So now I've got y times x minus 2 equals 4x plus 3. And finally, I can divide both sides of x minus 2 to get y equal to 4x plus 3 over x minus 2. And so then finally, our inverse function, f inverse of x, would be 4x plus 3 over x minus 2. Fun fact. Interesting. I mean, not fun. Important fact. When you find an inverse function, you're literally interchanging the role of x and y. So one thing that also gets interchanged is all the x and y things, meaning the domain and the range. So this function here, let me ask everybody, for this original function f of x, what's missing from the domain? What number is definitely not in the domain for f of x? You show me on your fingers. And I know you have enough fingers to show me what's not in the domain. Nobody? I think, yeah, I see some fingers. Yeah, 4. 4 is not in the domain of that function. Let me ask you a different question. This function, 2x plus 3 over 1x minus 4, definitely has a horizontal asymptote. And the horizontal asymptote would be y equal to 2, because the leading coefficients, right, the degree on top, degree on the bottom, same, leading coefficient is 2 over 1. So I'll point out that although you can cross the horizontal asymptote, in this particular example, we don't. 2 is definitely not in the range of this function. And what's super cool is that this inverse function has the opposite things being true. In this inverse function, 2 isn't in the domain and 4 isn't in the range. So they've literally switched. which is how some people then go on to talk about how you find the range of a function. You can totally find the range of this function by finding the domain of its inverse. So the domain of this inverse function is everything but 2, which is also the same as the range of the original function. Kind of cool. Not what we're here to really talk about today, but something worth noting is that that's how people often go about finding the ranges. If, and it's a big if because it's not always true, but if the function is invertible, again, not every function is invertible, but if the function is invertible, then you can find its range by finding the domain of its inverse, which is useful. Last one here. Last one for now. Find the inverse of 2 to the x minus 1 plus 3. All right, same process. I'm going to start with y equals 2 to the x minus 1 plus 3. And then I'm going to rewrite it as, I should say not rewrite it, I'm going to interchange. I'm going to interchange. But you can say switch. I like interchange better. I don't know why. X equals 2 to the y minus 1 plus 3. I'm trying to solve for y. I'm definitely going to have to use a logarithm at some point. Because 1, the variables in the exponent, or 2, we know the inverse of an exponential function is a logarithmic function. There's 2 ways to get there here. Either way, though, to get there, we have to isolate the thing that is raised to a power. So the first step we should do when we're trying to solve for y is subtract 3 from both sides. So I'm going to have x minus 3 equal to 2 to the y minus 1. And now you have a choice. You could take which log of both sides. Which log would I probably choose? I would choose the natural log. Here I might not, but yes, you could totally take the natural log of both sides. But I would say actually the route I would probably consider taking here, because it's a better display of the inverseness of the function, is to do the log base 2, or to just rewrite it as a logarithm expression. So I'm going to rewrite as log base 2 of x minus 3 equal to y minus 1. I feel like that's a nicer thing to do. And then finally, we got to add 1 to both sides. So y is equal to log base 2 of x minus 3 plus 1. And that is our inverse function. So our f inverse here of x would be log base 2 of x minus 3 plus 1. And again, since it's kind of there and not too terrible to see, if you think about, I'm going to grab my paper here. Sure. Paper, do I have paper? Yeah, somewhere, maybe. Fine. I want to point out, if you were to graph these things, 2 to the x minus 1 plus 3 looks like your usual exponential graph. I don't really need to graph these things. I just want to show you something real quick. Shifted up by 3 and right by 1. I don't really care about the right by 1. Kind of looks like that. Whereas your log base 2 of x minus 3 plus 1 looks like it's been shifted to the right by 3. Sorry, you can't see that at all. Apologies. It kind of looks like this. Oops. Not like that, James. Kind of looks like this. Here's your f of x. Here's your f inverse of x. Again, very, very generically, right? I'm not doing like a super precise job of drawing. What I really want to show you is this graph here, this f inverse, the domain of this is x being bigger than 3, or if you prefer, everything from 3 to infinity. Whereas the range of this original function is the same as that. The range here is exactly everything from 3 to infinity. So I just want you to see another example of how the domain of one of these functions is the same as the range of the other one, and vice versa. So the domain of this is equal to the range of that, and the domain of this is equal to the range of that. Here, the domain of this is everything, the range of this is everything. They are the same. It really comes back to saying, for inverse functions, all the x and y things just switch. That's it. So everything that's true for an x thing in the original function, it's true for a y thing in the inverse function, and vice versa. Okay, so that's inverse functions briefly. The other thing we're talking about for the last Sure, 15 minutes. Yeah, 15 minutes. All right, plenty of time. Not plenty of time. The difference quotient. It's just a fancy name for the slope of a line between 2 points. But the points we're going to label in kind of a special way. So I look at my, yeah. We could label, so I'm looking here. I'm going to call that A. Call that B. And then this Y value would be F of A. And this other Y value would be F of B. So if I want to find the slope of that line that goes to the point A comma F of A and B comma F of B, it's just the difference in the Y's over the difference in the X, just like the slope formula has always been, right? Y2 minus Y1 over X2 minus X1. So you can say, in fact, we can write that down, Y2 minus Y1 over X2 minus X1, which in this particular case is F of B minus F of A over B minus A. However, there's a preferred way to write. So you'll see this in your calculus class as well. And some people are going to do it more like this. It's unfortunate. Hopefully, most people are going to do it more like this, where we're going to say that this point here is actually, we're going to call it X comma F of X. And the second point here is going to be X plus H comma F of X plus H. So then if we want to find the slope, well, again, it's just Y2 minus Y1 over X2 minus X1. In this case, that's going to be F of X plus H minus F of X all over X plus H minus X. And in the denominator, we can actually do some subtracting and say that X plus H minus X is just going to be H, because the X's will cancel. So the difference quotient, we typically like to think of it as F of X plus H minus F of X all over H.
What's the second point?
Fair, yeah, I was like, that's a good call. That is my F of X plus H. So it's just the Y value I get when I plug X plus H into the function. So it's also that right there. But again, yeah, I know brain's a little small. So you can see that a little bit better. Other questions about this? Something I want to point out because it comes up kind of often. This is not the same as F of X plus H minus F of X all over H. That's a different thing. Because if I look at this thing here, what could I cancel on the top? Not the H, actually, not yet. I can cancel the F of X's, because F of X minus F of X is 0. And now I'm left with what? Right, I'm left with H divided by H, which is 1. And the thing is, when we do this process, which we're about to do, you should never, well, with one exception, you should never get an answer of 1. Your answer should always be more complicated than just 1. So let's look at some examples. So the idea here is that we're going to take some functions, not with numbers, we're not going to actually find an actual numerical slope. We're going to find an expression for the slope between 2 points that are just kind of an X and an X plus H. Here's what I mean. Now, this first example is not going to be terrible because we know what the answer should be already. So our function is F of X equals 5X plus 3. And let me just ask everybody, if I'm on the line 5X plus 3, which looks kind of like this, and I pick a point here and a point here, and I find the slope between those 2 points on the line y equals 5x plus 3, what should the slope between those 2 points end up being? Right, it's going to be 5. Well, let's actually do it for an x and an x plus h, and an f of x and f of x plus h. Okay, so when someone asks you to find the difference quotient, or I should say, simplify the difference quotient, your ultimate goal is to cancel out the h that you started with in the denominator. So every time we're simplifying the difference quotient, our goal is to cancel, specifically, we've got f of x plus h minus f of x over h, is to cancel that h. We want that guy to go away. That is always the goal. Why is that the goal? Because later on in calculus, you're going to let that h be 0, and we can't divide by 0. So we want it to go away before we try to make it everything else 0. That's what we want. But now it's just an algebra problem. So let's see. I've got f of x plus h minus f of x all over h. And I'm just going to substitute into my function 5x plus 3. I'm going to get 5 parentheses plus 3, where x plus h is going in the parentheses. Minus, we'll be careful here. If I write just f of x, which is 5x plus 3, that's not quite correct. So it should be minus all of f of x, meaning I really need some parentheses around all that. So make sure to distribute the minus sign. And then in the denominator, still h. So here's how this is usually going to go. You're going to simplify the top, and hopefully all the things that don't have an h in them will cancel out. Let's take a look. So I distribute this 5. I've got 5x plus 5h plus 3. Distribute the minus sign, minus 5x minus 3, all divided by h. 5x minus 5x is 0. Those go away. 3 minus 3 is 0. Those go away. So I end up with 5h divided by h. And now, since everything in the numerator has an h in it, there's only one term, I know, but I can divide the h by the h, and those will just divide out to be 1. So 5h divided by h is 5 times 1, which is just 5. And look, we got the answer we thought we should have gotten. The slope between those 2 points was 5. Great. Okay, next example is a little more complicated. Next example isn't going to be numerical. I know I said the answers weren't going to be numerical. This is an exception. Most of the answers will not be numerical because on a parabola, the slope between the 2 points you pick really depends on the points, right? If you pick like a point up here and a point down there, you've got a negative slope. If you pick a point like here and a point up there, a positive slope. So it's really going to be dependent on what points you pick, meaning our answer is going to have some variables in it. Which is fine. That's expected. So we're going to write out the whole thing. I encourage you all, at least at first, to keep writing out f of x plus h minus f of x all over h before you do anything else. You might even, if you prefer, over here, write out what f of x plus h is. So f of x plus h is 4 times parentheses squared, 5 times parentheses, plus 1, where the x plus h is going in the parentheses. So that's all of what's going to go in for f of x plus h, minus all of that for f of x, all divided by h. So it's a little much. So 4 times x plus h squared plus 5 times x plus h plus 1 minus parentheses, because I have to subtract all of it, 4x squared plus 5x plus 1, all divided by h. Okay, the ultimate goal, cancel out that h in the bottom. The intermediate goal, hopefully everything in the numerator that does not have an h canceled out. Or in other words, we want everything in the numerator that's left behind to have an h, so that we can then factor out an h and cancel the h to the bottom. So I need to multiply stuff out here. X plus h squared, or x plus h times x plus h, is x squared plus 2xh plus h squared. And there's still a 4 out in front. I can distribute the 5 here and get 5x plus 5h plus 1. And distribute the minus sign, we got minus 4x squared minus 5x minus 1. What's one thing I can cancel right now? Shout it out. Yeah, 5x and negative 5x. What's another thing I can cancel? 1 and negative 1. Awesome. Great. So then I need to distribute the 4 here. So I'm going to have 4x squared plus 8xh plus 4h squared plus 5h minus 4x squared, all divided by h. And now the only other thing left to cancel is the 4x squared. 4x squared minus 4x squared is 0. And now every remaining term in the numerator has an h in it. So you can either divide each thing by h and just say you get what you get. I prefer to take the path of factoring out an h from the top. So I'm left with an 8x plus 4 times h to the first plus 5, all divided by h. And then this h divided by h is equal to 1. So I really just got 1 times 8x plus 4h plus 5, which I should have really just skipped that step and written 8x plus 4h plus 5. And that is our answer. That is what the difference quotient simplifies to in this particular problem. And that's where we stop. There's nothing else we can do. Later on, when you take calculus, you'll then take the limit of this as h approaches 0, and you'll see that the derivative of 4x squared plus 5x plus 1 is equal to 8x plus 5. But that's a story for next quarter. So if all those words I said don't make any sense to you, that's totally fine. They shouldn't necessarily make any sense to you yet. Okay. So they get a little bit worse. We probably don't have time for both of these, but we'll certainly do the first one. So I want to simplify the difference quotient for f of x equal to 3 over x. And I'm just going to, I think it's a good plan to write down what f of x plus h is. So be careful. When you write down f of x plus h, you're not just adding on an h at the end. You're adding an h to where x is. So instead of writing 3 over x, I feel like I didn't say that at all. I'm substituting in x plus h for where x is a better way to say that. So f of x plus h should be 3 divided by x plus h. Should not be 3 over x and then plus h after that. All right. Algebra time. F of x plus h minus f of x all over h. So I've got 3 over x plus h minus 3 over x all divided by h. That doesn't look fun. I'm gonna subtract some fractions. And subtract fractions, I really need a common denominator. So that's what I have to do. So I'm gonna do, actually I get rid of it. So 3 over x plus h times x over x minus 3 over x times x plus h over x plus h, all divided by h. Okay, so then here's one thing we're going to do in the next step to make it a little bit easier. So don't write yourself a big fraction for the next one yet. So I'm going to have 3x over x plus h times x. I don't necessarily think you want to multiply that out, although you can. Minus 3 times x plus h over x plus h times x. And instead of dividing all this by h, dividing by h is the same as multiplying by what? Exactly. Thank you. That way I don't have to write like such a fraction over fraction kind of thing. So now the whole reason for getting a common denominator was so I could combine these two fractions together. And I'm going to rewrite this part as one fraction. The denominator is going to be x plus h times x. And on top, I'm going to have 3x minus all of this. So it's really a 3x minus 3 times x plus h times 1 over h. I could probably put that h in the denominator now because fractions, when you multiply, you use top times top, bottom times bottom. So I'm going to rewrite this as 3x minus 3x minus 3h. I distribute the minus sign. All divided by x plus h times x times h. And again, I know that this h is the thing I want to cancel out. Any other h is not a problem. It's just that first h that happens to be in the denominator, that is the one that needs to get canceled every time. So 3x minus 3x goes away. Oops, sorry, too many pens. We're left with a negative 3h over x plus h times x times h, and then h divided by h is 1. So we have a -3 over x plus h times x, which you could leave like that, or if you prefer, you could write it as -3 over x squared plus xh. Either way would be totally fine. And that would be our simplified difference quotient. Simple as it gets. So again, when you're simplifying a difference quotient, your goal is to make sure that the h that you started out with in the original expression cancels out. We won't have time for this last one because it is 10:51, so I should stop talking. But I will say that I think there's a video of me doing this one on Canvas already. If there's not, I'll post one just so you can see it. I don't think the problems that are on the homework are as complicated as these last two, but they're good examples because you definitely will see them in calculus. So I felt like I couldn't not show them to you. But I didn't show you one of them, so I'll write this one down. This will be in the notes for you all to see later if you want to look at the notes as well. All right, I'm gonna write it down right now. I got time. So if you're on Zoom, you can stay and watch me do this. If you want to stay and watch me do this, you can, but you're certainly obviously all welcome to leave. But I'm gonna write it down because I should.
I have a question about the homework.
Yeah, what's up?
Are we supposed to receive like extra credit on it? Like when we first started? I don't know. I remember seeing extra credit on the homework assignments.
The homework assignments.
Now we're just recently like took it off. So
Oh, no, that was an extra credit. So what that was is that the assignments were not, the number of points on the assignments were not matching with the number of points on Canvas.
oh
Yeah, so I was correcting that. That was,
okay.
yeah, there was no extra credit. They were not correctly pointed.
That makes sense.
Hey, what's up?
I'm doing like my course registration stuff right now. I was
Okay.
wondering which course I
Well-
should sign up for after this.
It depends on what your major is.
Thinking about going the 17A route
Okay, well then 17A would be the class you take after this.
after this.
Yeah.
Like, I don't have to worry about taking another like.
Typically
preparation
not. This
class.
class should be adequate preparation for taking either the 16 or the 17 series. I
Okay.
do highly recommend signing up for one of the 17A code classes. That's
Okay.
offered next quarter.
Thank you.
You're welcome. Yeah, what's up?
I'd just like to know what was the answer for this week.
Oh, sorry. Yeah, that was, well, so then we just divide each thing by h. So we get 8x plus 4h plus 5.
Okay.
Yeah.
What's behind your face screen there?
My what thing? Oh, sorry. Yeah. Sorry about that. I know it's always the problem with having that there. And I guess I should say for the video that's still recording, since I'm gonna leave this up anyway. The idea here is that when you have a square root minus square root, you multiply by the conjugate of those things. So that then you get the first thing squared, which is 5 times x plus h plus 1, minus the second thing squared, which is 5x plus 1. And then we distribute the minus sign, we multiply it out. Everything that doesn't have an h on the top cancels, as we hope for when we do this kind of thing. And then finally, this h divided by that h is going to equal 1. So we end up with just 5 over square root of 5 times x plus h plus 1, which I guess you can multiply it as 5x plus 5h plus 1, but you don't really need to, plus the square root of 5x plus 1. And yeah, it's kind of a gross answer, but that is the answer.